So, before we get started properly, I'd like to briefly go over what the point of this talk is, why I'm here presenting this for you. As you may have noticed, the subtitle for this talk is Below the Root. This is an ancient 8-bit game that... Excellent. I'm sure most people like me are more interested in the nice 3D chat rooms nowadays, like World of Warcraft. The key point that I want to get across is a lot of security focuses on, for example, privilege escalation to get root access to a system. So you can do whatever you want within reason, access protected resources. Such things as access control, segregation between data, between different processes, between different users, is implemented and architectured within the operating system itself. If you can run arbitrary code in the operating system, then you can modify arbitrarily what, for example, a user is. If you want to, you can change root, so root no longer has what you would assume to be root privileges. You can modify a system so any unprivileged user actually has all possible privileges, which is something I'll come on to later. This is quite a serious issue, really. I don't know how many people here are on the NT-Dev mailing list. NT-Dev's run by OSR, who are a driver development consultancy, and they deal with driver development issues, and I saw a couple of weeks ago someone posted on that as far as he was concerned, that all the major operating system issues were solved in the 60s when a large amount of operating system research was done. I would have one contention with this, and that's security, which to a large degree is being backported back into operating systems, and their implementation that was designed in the 60s has significant flaws that make doing such backporting it security quite a challenge. I would also like to say that anyone in this room, if they knew how to do it, would be able to own my laptop if you wanted to, and there's nothing really I can do about that, apart from minimize the possible surface, in which case, like I said, you can do whatever you want. You can access anything. If I have full disk encryption, if you're running code in the kernel, then that doesn't matter. You can either disable it or hook into the kernel so you can monitor what's being accessed and, say, set up a stealth port and network it back out to you. Anyway, stop. I'm going to go have a quick overview of protected mode and fundamentals of the NT-kernel architecture from a security point of view. I'm sure most of you are familiar with that, so I won't spend much time. Potential attack vectors, how you can get access from an unprivileged user into the kernel. Useful tools that I use when assessing kernel code, either from a black box or white box perspective. There are a few examples. I'll go over, show you the kind of things to look for. One of them is as yet unpatched, but I'm not going to say what it's in, obviously. Defensive measures, so how, if you're a developer, what the kind of things you should be thinking about if you're an operating system architect, the kind of issues you should be thinking about, and how to make the operating system more secure. And future directions for work, so research that I'll be doing or can be done into making our operating systems, and hence anything that uses computers, more secure. So, nearly 3 decades ago, Intel released the 8088 processor, which ultimately became the Pentium, which we use now, or Pentium clones, which are used nowadays, and is the most popular processor for certainly Windows-based operating systems, but is also useful for a wide variety of other OSs, such as Linux. For the 286, back in the early 80s, issues were identified in terms of operating system security and stability, and Intel implemented hardware-based protection. So there is a segment protection at the page level and at the segment level for memory. Specific structures to define how code could transition between different privilege levels within the processor. Different management of instructions so that sensitive or privileged instructions could be trapped or would cause exceptions if executed by unprivileged code. And 4 operating system rings, ring 0 to ring 3 being the least privileged, that would allow then the operating system implementer to implement a secure kernel that would provide access to hardware resources underlying that, and then provide services to the user mode code so the user can do what they want. The NT kernel itself provides segregation of processes. This is done by keeping a page directory for each individual process. An important issue, protection of the kernel from user mode. User mode normally can't access the kernel. The kernel memory will be marked as supervisor memory and will just cause an exception. But if the user mode, some user mode code requests that the kernel performs some processing on a buffer, then the kernel has to do that processing, and there is no distinction, or as far as the kernel's, there's no hardware distinction as far as the kernel's concerned between user mode memory and kernel mode memory. So the kernel has to have some other way of deciding whether a buffer is valid or if it's just being asked to overwrite arbitrary memory. Up until Windows Vista, the graphics subsystem was entirely in the kernel. That's changed for Vista. I'll come on to that later. And there's also session management for terminal services. The NT kernel, as I said, has to provide services to user mode code for hardware management and internal operating system management. System calls are well known, well documented, so I'm not going to talk about them. Device I/O control, there are several papers on that and how to hook that to monitor I/O control code sent into the kernel. The only thing I would add with that is there are some issues beyond. Most people will sit there and the NT kernel supports 3 different I/O modes, buffered, direct, and neither. And most people say, you should look for the neither, because that means the kernel will get the pointer directly from user mode, and if they don't validate it, then you can pass a pointer into kernel memory, and may be able to overwrite arbitrary areas of kernel memory, or have data disclosure by reading arbitrary areas of kernel memory. Of course, if the structure passed in, if it's a direct, or if it's an MDL or a system buffer, then if that contains pointers, those pointers also have to be validated by the kernel code. Graphics drivers, not something that's really been discussed to my knowledge. There are APIs from user mode to pass data directly to graphics drivers in the kernel. This has changed slightly for Vista, as I said. There are 2 functions, draw escape and exit escape, which are very similar to device I/O control. And as I said, any data that's passed up to the display driver needs to be validated. There is the paper that accompanies this talk has much more technical detail if you're interested. There are, of course, the kernel networking components, NDIS and TDI, to provide transports and interfaces to the underlying hardware. And on Vista, the Windows filtering platform and the WinSock kernel for to allow kernel mode network filtering, so firewalls. Port objects, I haven't seen much talked about. Port objects are part of the installable, the file system kit. So they're for file system developers, and they allow communication between file system filters and user mode to kernel mode. They have a slightly different interface to the other typical user mode APIs, but they're fairly similar. Essentially, they're just wrappers for some standard user mode APIs. The Windows driver framework, I'm not going to cover much. There's more detail in the paper. The Windows driver framework was developed by Microsoft to simplify kernel development under Windows. As I hope I got the point across, any third-party code in the Windows kernel is obviously going to increase the likelihood, well, is going to increase the attack surface for unprivileged users or remote code execution in the kernel, which is quite serious. So the WDF what has been implemented by Microsoft and is essentially just a wrapper for the older Windows driver model to simplify and help reduce the attack surface and the typical coding errors that happen in kernel mode code. Going back to graphics drivers, the main reason Microsoft moved one of the kernel components from kernel mode to user mode is, according to their own statistics, 20% of the blue screens they receive actual data on are caused by display drivers. There are also kernel mode callbacks for things like registry access, process creation, image loading into memory, and typical hardware interfaces. So either communicating with hardware, either via mapped memory, or internally by using the low-level instructions, for example, on the x86 architecture in and out, so doing port I/O. And listening to hardware, which is typically triggered by hardware interrupts, which a device driver will keep a context of and then pull any data up from the hardware. So, given that outline of the architecture, what could we do from user mode? Is there the possibility of going directly from user mode to kernel mode just by circumventing the protection mechanisms in place? There has been some talk recently, particularly by Theo de Raadt, about CPU bugs and their exploitability. I don't know of any that could be considered traditionally exploitable. I know someone at Symantec who's done some research, and apparently there are CPU errata that allow untraceable code to be created, but I haven't verified that myself. In the paper I mentioned a couple of interesting ones that allow possibly arbitrary memory access, but these are quite abstruse, and for some reason the Intel and AMD aren't actually that keen on giving out the details. Beyond that, there's also the issue of operating system design itself. If there is a flaw in the design, then that is going to allow unprivileged code access to, that may allow unprivileged code access to kernel structures or code. The best example being Windows 95. So if you are familiar with the protected mode model, the GDT and I believe the IDT were in the user mode portion of the address space, so were directly writable by a user mode process, so trivial to exploit. Public APIs, I've mentioned a few earlier. A lot of these are well known, typical ones like Start Service, Device Error Control, or Xescape for talking to display drivers. Undocumented APIs, well, publicly documented APIs, or documented by Microsoft, but have been documented by other people who are either reverse engineers or security researchers, such as ZW System Debug Control or ZW Set System Information, which provide interfaces for controlling the kernel debugger, apart from Vista, which has changed, and internal NT management. There's also the possibility of architectural flaws. I've made a distinction between architectural flaws and bugs in the code, because kernel code is, as I said, is designed to provide services to user mode, and it may be a situation where a service is provided that is actually doing what it's supposed to do, but what it's supposed to do breaks operating system security levels. So a device driver, for example, in a rootkit disinfection system that can copy chunks of memory around from arbitrary areas, could be leveraged, obviously, to overwrite structures in the kernel and allow arbitrary code execution in the kernel. Bugs in the code, these are standard things, though there are issues with exploiting them. There is internally what could be thought of as a heap paged pull and non-paged pull, that due to the way the kernel works, that those are extremely instance specifics for exploiting. There's no way you can do something like heap feng shui, because if you just sprayed the kernel heap, you would have a blue screen pretty much instantaneously. Subverting operating system initialization. EI's boot root and the vBootKit have already been talked about publicly. The vBootKit talk, I think, has been pulled from Black Hat over here, unfortunately. But if you're interested in that kind of thing, then you can refer to that research. Something else not normally talked about is actually modifying the kernel modules on disk. You need to have some privilege level to do this anyway, but I used to work in antivirus, and I've never seen a kernel module infecting virus, though there is no reason why there can't be. And kernel modules also support DLLs, so to speak, export drivers, which will be loaded up as part of their initialization. So the tools I use for assessing kernel code, I'd like to break them into two different areas depending on what I'm doing: static and dynamic analysis. Dynamic analysis, by that I mean runtime analysis, so tools that monitor what's going on, that can actually probe a driver in the kernel at runtime. And static analysis, disassembler, or source code auditor. Dynamic analysis can never guarantee results, and because if you do hit a bug in kernel code, it will cause a blue screen. Fuzzing can be awkward to automate. I'll mention some ways that you can later on, though it still is awkward. Static analysis allows you to cover every potential path of execution if you want to, but that's obviously time-consuming, and if you only have a binary, as I sometimes do, then that can be quite complicated as well. Microsoft provide several tools for kernel developers to help them assess their own code, and some of these tools will be used when the device driver is submitted for certification by Microsoft. So it will have a certificate particularly useful for Vista, which has a mandatory code signing policy. They have the SDV, the static driver verifier, which requires source code and will check for typical bugs in the code, so null pointer dereferences, race conditions, and things like that. Prefast, which is fairly similar. Disassembler, I typically use IDA because it's pretty much the best disassembler out there. And the Windows Driver Kit, mainly for the information it contains that's more difficult to get hold of, particularly the header files that provide you documentation on the structures in the kernel and things like that. Dynamic analysis. I do occasionally have discussions with people about which debugger to use. It's obviously a question of personal choice. I use WinDbg almost exclusively nowadays. It is, as far as I'm concerned, the only suitable kernel debugger for Windows. Granted, you have to run it in a remote setup with one computer debugging another computer, or a VMware, virtual machine VMware or virtual PC, which can be more awkward, but that has the added bonus of having greater stability for the operating system because you're not running the debugger on the same machine. Plus, the integration it has with Windows makes life an awful lot easier. The driver verifier is an internal component of the Windows kernel. It can be enabled to verify random drivers or specific drivers, and will do things like emulate low memory conditions or randomly fail APIs. There are other various tools I use to extract information, such as WinOb from sysinternals, which allows you to browse the kernel's object directory, so you can check ACLs and things like that. NT-dispatch points. Access will go and read device driver's dispatch table. So if it supports the IO control interface, you can find where those entry points are in the kernel, and then either fuzz them or analyze them statically. And rootkit hook analyzer from resplendence.com. This is an interesting tool. Not only does it find hooks in the kernel, it also allows you to fuzz them if you want. It comes with the obvious disclaimer: if you fuzz this and it finds a bug, then it's going to crash. So that can be quite useful if you're going to do some fuzzing analysis on hooked system calls. The only other issue with that is it only fuzzes system calls, so it's not going to fuzz any other hooks that are potentially there. I'll come into other possible hooks later on for when talking about PatchGuard briefly. So I've gone over the tools and the architecture. We're looking for poor access control, so functions that should not be functions or structures such as shared memory sections that should not be accessible by unprivileged users. This can typically be mitigated by checking for specific privileges in the kernel, because when a thread transitions to kernel, does a system call or whatever and transitions to kernel mode, it's still running as the same process. So you can put access control such as a debug privilege if you want, or TCP privilege, a trusted computing block, I think, and just check for that. Trusting user-supplied data, I already mentioned this, pointers and lengths, this is a typical issue. As I said, any buffer that's passed in that that has pointers or structures contained within it that have lengths, that has to be verified by the device driver itself. Microsoft, for the updated documentation for the Vista display architecture, specifically say there are several APIs that you have to validate the data that's coming in for if you're going to use it as a length or as a pointer. There are typical coding bugs that you'd expect for user mode code, such as boundary conditions or off-by-one errors or signness issues. These are typically more difficult to exploit, as I said, if you if you overflow the paged pull or non-paged pull in the kernel, then you've got very little idea of where that is or what you're overwriting, so likelihood is it's going to go down immediately. Of course, if this is accessible over a network, then that's still pretty good. If you can, say, have a UDP broadcast packet and just take down a whole bunch of machines, that's pretty serious. And as I mentioned earlier, design flaws, so exposing kernel functionality or data to user mode, which shouldn't be done. I would add that there's a paper on uninformed.org assessing Kaspersky antivirus, and they mentioned several instances where kernel data and functionality is exposed to user mode, to unprivileged code, and shouldn't really be. Static and dynamic analysis. I'm a reverse engineer myself, as you saw at the start. I'm not here to tell you how to do that. There are plenty of courses, talks, and books on the subject if you're interested in it. I find it beneficial because you know you're going to get code coverage. You can find all the entry points into the kernel code and then manually audit them, check if there are any particular issues. I mentioned signness. Subtle bugs are easy to find. Signness issues are blatantly obvious in a disassembly under x86 or x64 because the instructions are actually different. Memory overwrites are really trivial to find because memory access is pretty obvious. It might be a more subtle bug if someone's setting a particular entry in a data structure, then that may be less obvious that that's controllable from user mode if you're doing a source code audit, whereas in a binary, you can just follow it through. If there's a large amount of kernel code, then obviously it's going to take a huge amount of time, and reverse engineering can allow you to focus in on the particular areas that you're interested in. So if it does kernel mode hooking, then you can say, okay, it's hooking these APIs, I can then fuzz these APIs. So it can help speed time, help you speed things up by finding areas to focus on for more dynamic analysis. As you're not actually running code, you're never going to cause the code to fall over, so there's no need to analyze crash dump, which can be awkward, particularly with some of the more arcane issues that are associated with kernel mode security, such as race conditions. However, the lack of symbolic information may be difficult. If you only have a binary with no symbols, then you've got no additional information. Source code can be greatly helpful in that case because you've got at least some idea what the person who wrote it is trying to do, though there are also the typical issues associated with source code review. Naming a variable often gives the intention of what that variable is supposed to be used for, but that doesn't mean that is how it is used. A programmer could bring in assumptions he's making that then are invalid or can be broken. And if he follows those assumptions, then you won't find those bugs. Source code analysis. Access to source is not common. If you're doing an internal audit for your own company doing a device driver or product that requires a device driver, then obviously you're going to have it. If you're a researcher or doing a black box test, then obviously you're not going to. With a suitable IDE, it will greatly help you speed up the process. As I said, assumptions by the coder may make things difficult. The source code auditing tools available and the verification tools from Microsoft help. And as I say, you can always do the typical code review tricks of searching for things like assume or hope or break. So once we've found our bug in the kernel, what can we do with it? Targets we're interested in are static or object function pointers. Static pointers will be pointers to kernel mode callbacks that may be initialized. The object function pointers in the object directory in the kernel. The kernel is, in a sense, object-orientated. Objects have an object header, associated data, and associated function pointers in a similar way to C++ objects. If you find the object in the object directory, then you can overwrite the function pointers and then point that to your encode in user mode or wherever and call that, and it'll be running as the operating system. Kernel variables, I mentioned at the start, the kernel needs to make a distinction internally between user mode and kernel mode memory, and it does that in Windows by one single variable, user probe address. So when dealing with buffers from user mode that are verified internally by the kernel, so if you're using buffered I/O in the kernel, then those pointers will be validated against user probe address. Typical protected mode descriptor tables, the LDT, GDT, and IDT. The IDT is an interesting one because the several interrupts are accessible from user mode, particularly int4 and int5, the divide by interrupt and overflow, and the bounds error. Especially since they're unlikely to be triggered in usual operating system access. If you have a null point, if you can overwrite to a null value to an arbitrary address, then you can overwrite to the IDT the offset for int4, for example, trigger an interrupt, and then it will continue execution at 0 in virtual memory, which is in the user mode address space and can be allocated up. Return addresses, these are more difficult to find, so there's typical buffer overflow issues. GS is now enabled by default for the Windows driver kit. That doesn't mitigate all issues. GDI for the functions that pass up data to the display driver. If the buffers are smaller than 64 bytes for draw escape or 32 bytes each for exit escape, are just allocated on the kernel stack, both the input and the output buffer. So if data length isn't being validated in the kernel, there's the possibility of the display driver then overwriting the stack address for Win32k, and that is not protected by GS, by stack cookies. You can overwrite code from a kernel module. I don't know for sure whether it's the case on all versions of NT, but I've looked at SP2 and Vista, and kernel memory is writable by default. The I/O access map from the task state segment. This controls access to the instructions in and out. So if you can overwrite that, find that and overwrite it, then that will allow you to use the privileged instructions in and out, which can be used to interact with hardware. Also, any kernel structures. I have a demo later on which will find the process token for the parent process of and modify that in memory, changing the process pointer to the process token. That's elevating the parent process from unprivileged user, in this case to operating system. The loaded module list, if you're writing a rootkit, or another example, the LUIDs used to define the actual privilege values. So SUDB privilege or SUTCB privilege are just internally numbers. If you find that table and overwrite that with values that is just a privilege that's available to all unprivileged user mode processes, then all unprivileged user mode processes all of a sudden have all privileges. So, real-world examples. These are all bugs I found recently. The kernel runtime library exports functions to support compression, LZ compression in the kernel. This is used by server message block code and NTFS for file and folder encryption. Internally, it takes a parameter that indicates what particular version of what particular flavor of compression to use. Only LZ is supported, though it was designed to be extensible. This is used as an index into a function table. There are only 8 entries provided. However, the maximum value allowed is 15, so obviously there are 8 other entries that are undefined, and depending how the compiler actually builds the executable, may be code or may be data, and those, whatever's there, may point into user mode and can therefore be trivially exploited. The issue with this is NTFS. The only way to access it is actually through NTFS, and that means modifying NTFS metadata directly on the disk. And to do that, you need to be admin or have physical access and a USB key, and that's not really a security issue. That's the exploitable code, as you can see. It masks it with it checks this 15 and then uses that as an index into this jump table, and these can be treated as pointers by the kernel mode code, and several of those are into user mode addresses. This is on disassembly from the Vista x64 kernel. All the bugs that I'm going to talk about have a greater deal of explanation in the paper. Following code is an example of a typical kernel mode issue. It takes a pointer from a buffer and just trusts it. The original version of the code I found this issue in either sign extended a stack address and then wrote it back to the pointer you supplied it, or wrote an internal handle there. The most recent versions I've checked just write the handle. So obviously some issue has been noticed there by the developers, but not addressed completely. This can be used to overwrite other code or data and allow arbitrary code execution. Key point being here, any pointers from user mode should be validated or should be treated as opaque, such as the handles the kernel itself uses for files, which are internally treated as indices into a handle table, but are not actually treated as direct pointers. I do actually have a proof of concept for this, which I'll go through briefly. If I could type. Yeah, so I'm a standard user. As it happens, that user is actually admin, but this will work with an unprivileged user. Sure. Well, I could do that, but probably change the font. There you go. So, standard user, admin user. This will exploit an actual bug for a driver that on a hardware on a system, which is why I'm not running this in a VM, because VMware doesn't currently support emulation of actual hardware beyond the processor, so you can't do things like running a system. As I said, this just swapped the pointers to the process token in the eProcess structure in the kernel. And now this command prompt is running a system, so I have access to resources that the system process does, which is everything. This is the actual exploitable code in a modified form because it's as yet unpatched. This is where the sign extended stack address is written back to the user mode control pointer, which is in ECX. So it writes to ECX and ECX plus 4. Where the handle is written is not in this particular piece of code, but which is the actual vector for the exploit in this case. Trivial to find. This is more of an architectural issue. As I said earlier, there are sometimes some specific functionality is exposed to user mode which shouldn't be, or should only be exposed to privileged users. This is an arbitrary memory copy. In this case, fuzzing wouldn't have been much help, though it's just, exposed by the I/O control interface. The structures that are passed into the kernel are quite complicated. There's several substructures, and it's unlikely to be hit in a meaningful way by a fuzzer. In this case, either access control to the driver, so as I said, a TCP privilege, or a different architecture is needed. And very typical stuff. It processes the data, gets pointers, and then right down here, it just does an optimized copy from to user mode specified address to a user mode specified address. So how can we deal with these particular types of issues? First of all, as I said, parameter validation. This is an issue based on the documentation Microsoft provide now in the WDK that obviously Microsoft are aware of, based on my experience of driver code and device driver writers, not necessarily as widely appreciated as it needs to be. Code signing, as I said, Microsoft have introduced mandatory code signing for Vista. However, there is a question whether this code signing necessarily enforces code quality. And also, there are issues related to revocation. I don't know if anyone here has noticed, but last week someone released a tool on rootkit.com which had a signed driver, which then would load a user-specified unsigned driver into the kernel, thus bypassing the code signing quality. How do Microsoft deal with this? There is revocation. They can now revoke code signing certificates, but when do they do this? Do they do this every Patch Tuesday, allowing the stolen certificate to be used for a month, possibly, to sign rootkit drivers? Or do they do it as soon as possible and push it out through Windows Update? PatchGuard. PatchGuard is another system introduced to try and a lot of people have looked at this from a security point of view as if this was in some way dealing with rootkits or malware in the kernel. I personally don't see it as that. It's a case of Microsoft trying to take control of the kernel, so they have more control over what goes in and therefore can have better control over the stability of the operating system and other security-related issues. PatchGuard has been fairly thoroughly discussed on uninformed.org. There's very good paper, well, two very good papers on there if you want further material. However, not all possible kernel mode structures are protected by PatchGuard. As I mentioned earlier, the objects in the object directory in the kernel all have function pointers. Those aren't protected. So it is still possible, well, quite trivial, to implement a rootkit that can hook the NDIS driver or the file system driver or any file system filter drivers and redirect the output and modify the output arbitrarily. Therefore, so you can still do network stealthing and exfiltration and file system filtering. Process manipulation is more difficult because those are implemented still by system calls. But it's not the thorough overarching solution to preventing PatchGuard in the NT kernel. As I mentioned earlier, Microsoft have moved some of the functionality in the kernel in Vista to user mode. So they've created a user mode driver framework, which is used typically for USB drivers, which provides a standard interface. So the actual third-party driver runs entirely in user mode and just accesses the services provided by the driver, thus reducing the amount of third-party code running in the kernel. Obviously, this has also been done with one of the components for the display drivers in Vista, and some of the actual internal Windows architecture has been moved from the kernel as well. We can restrict access to APIs as well, so based on the user, their privilege level, or privilege restrictions and process restrictions if need be. But that's only with the current architecture. And as I said, the design architectural solutions created in the 60s don't necessarily address the typical security problems that are faced nowadays. And it's awkward to backport the security into them. So there are alternative approaches. A lot of work has been done recently with virtualization and hypervisor. This has typically been done with rootkit work. There's talk after this, which is, I believe, related. Designed to help virtualization on a processor, so you can run different isolated operating systems on the same chip. Provides a layer beneath or above, depending on how you want to think about it, the supervisor of the operating system itself. And it could be used, in essence, to provide a microkernel architecture, so running the operating system underneath as less privileged, and then controlling that within the supervisor. However, that's quite difficult to implement, and a microkernel could just be used in itself. Microkernels hit the public really in the early 80s with a Mac operating system, which was a research operating system at Carnegie Mellon University. More recent operating systems do use it, such as Symbian and Minix, which is a version of Linux, I think, or Unix. It doesn't require any extra hardware for virtualization. And the key point in terms of security for a microkernel is it reduces the attack surface available to unprivileged code in user mode by only providing a bare minimum of hardware management that's absolutely necessary. And then the servers themselves that interact with this functionality run purely in user mode. For example, Symbian, the majority of the file system code runs entirely in user mode. This also increases flexibility with the architecture that will be allowed with the microkernel, so there's no specific architectural constraints, such as, for example, the WDM, the Windows Driver Model, or the WDK provided by Microsoft to interact with the NT kernel itself. Though this can be more awkward, it can make design and implementation a more lengthy process. An excellent example of modern microkernel is Microsoft's Singularity, which is a research operating system. It's strongly typed and uses entirely software-based protection. So the actual kernel itself runs entirely in Ring 0 as a supervisor and relies on software-based protection mechanisms to ensure that no code does what it shouldn't be allowed to do. So, future work. Some of you may well have seen this, especially if you've been using Windows for a long time. As I said, the big issue with fuzzing is what happens when it blue screens. The crash recovery and analysis really needs to be automated. There is always the possibility of running a VM and scripting the VM to reboot and pulling off any crash dumps from that. As I mentioned earlier, what about real hardware? You can't, at the moment, interface a virtual machine with hardware installed on the host PC or virtualize the hardware itself. It's possible to have bug-check callbacks. These can be registered. The problem with those is if the kernel is seriously corrupted, then those won't ever be called because the machine's pretty much screwed. Or it's the possibility of modifying the kernel itself, either dynamically or statically, modifying the binary or the code at runtime, in a similar way to provide a bug check callback, but that suffers from the same issue. As I mentioned earlier, fuzzing is greatly aided by some form of static analysis. I had hoped to release some tools during this talk. They're not finished yet, unfortunately, though I'll talk about them later on. But Ollie Whitehouse at Symantec has created a tool called SwitchFinger that I'll release soon, and that will scan a binary for specific signatures for the switch tables, which are used to implement I/O control interfaces, for example, thus greatly speeding up the location of the possible entry points in kernel code. Virtualizing the kernel. This is one of the tools that I'm working on. To avoid blue screens, quite simply, you run the kernel code in use mode. This is awkward, but doable. At the moment, I've got an emulation of the NT kernel that's about 75% complete and just exports the same APIs and has either faked functionality or the same functionality. Beyond that, you need to provide virtualized or at least faked I/O access, plug-and-play management support and process support. And you need to handle the privileged instructions. Generally speaking, no device driver should be doing things like accessing the CR3 register, the page directory base register, though there's nothing to stop it from doing that, especially if it's a rootkit, for example. So you need some way of trapping and handling that and returning appropriate faked values, though that's not that difficult because there's user mode support for exception handling. And add instrumentation for analysis and logging. So the idea is just have a tool which provides this environment, say, okay, run this driver, so the driver entry points run, and it will just dump out whatever particular entry points it finds, so any user interfaces to user mode, any shared memory sections it creates, for example, any hardware it tries to access. And then pass that back to the user so they can then obviously speed up their audit. Automated binary analysis is something I've been working on for a long time. It's a very difficult problem. Basically, model the CPU itself, and under the current implementation, instead of using registers, meta registers are used, which have a range of values, and those values, that range of values is then constrained by the actual code that's executed. This allows for, in theory, total code coverage, but that requires an enormous amount of state to be stored if you're tracing through different branches sequentially. Though if you are willing to rely on heuristics, then you can obviously search for specific APIs that are known to be have issues around particularly string handling APIs, and then just perform your analysis around that. Yeah. Conclusion. So I've gone over an outline of the kernel architecture. And the processor underneath, and the kind of security issues that I've seen and you are likely to see if you're a researcher or a consultant or developer, and outlines of how they can be exploited, and specific architectural implementations that could be used to mitigate them. The current NT-kernel architecture, as I've said, due to the large amount of third-party code and Microsoft code that's necessary in the kernel, provides a very large attack surface to user mode. So it's quite difficult to deal with this without re-architecturing Windows itself, which would be an enormous task, and why Windows has essentially had the same kernel since it was written in the late 80s. It's debatable how much effort has gone into securing kernel code. Obviously, Microsoft, due to their experiences with in the 90s and early 2000s have gone into a great deal of effort now to secure their code. The Microsoft code that I've seen that's been developed recently is all pretty good, really. However, third-party code, a lot of the developers I've seen when I've tried to contact vendors about bugs have either just treated it as a bug or not really been that bothered. As far as they're concerned, it's not a security issue. It's just a bug in their driver. The fact that potentially I could get remote code execution in the kernel on someone's box isn't that important. Some areas of the kernel have not received much attention. I mentioned display drivers. There are other areas such as network handling, which all could benefit with auditing. As I said, Microsoft have gone to great lengths to try and reduce the attack surface of Windows Vista, and will presumably carry on to do so for the next iteration of Windows. And there's a great deal of scope for further research and tool development. I've outlined two particular areas, but there's, in general, code review and with the specific problems related to the NT kernel itself and kernel mode code. There's an awful lot that can be done. And I would add one further point. The level of third-party code currently in the NT kernel pretty much guarantees that Windows NT as an operating system is going to be insecure. This was discussed also last week on NT-Dev. Someone is trying to develop a device driver that switches Windows. Basically, it will shut down Windows when you tell it to, and then load a secure operating system. There's a great deal of discussion as to whether this was actually doable. Is it possible to go from an insecure operating system into a secure operating system? And the general consensus was, which I agree with, no, you can't, because if there's arbitrary code running on there, that can always interfere with the process of transitioning from unsecure to secure by hooking into the kernel and subverting it. So, thanks for listening. Any questions? Yeah. Sure. The PatchGuard discussion is on uninformed.org. Can you read that? PatchGuard can, so the question was, how much does PatchGuard impact on security, and what difference would it make if it was introduced on 32-bit architecture? That's a tough one. Essentially, it will never be perfect. It will always be possible to circumvent PatchGuard. Microsoft can only make it arbitrarily difficult to do so. It's up to them in terms of how much effort they want to put into it, how difficult they might want to make it, which will obviously restrict the number of people who will be able to then circumvent it and do whatever they want, provided they don't release a programmatic way of doing it. I think any attempt to try and constrain code running in the kernel and minimize its impact and within reason what it can do is a good thing, but I don't think at the moment introducing it on a 32-bit platform would be a good idea, not least because of the amount of software it would break. The reason Microsoft introduced it on the 64-bit platforms, so 64-bit XP, Server 2K3, and Vista, is purely because the drivers would have to be rewritten for that anyway. So the issue of backwards compatibility isn't there. So I think it's a good thing, but it's not worth backporting to 32-bit. Any other questions? Yes? Yes, subverting the operating system bootstrap process, yes. Sure. So he's asked what are the typical ways to subvert the OS bootstrap process. A colleague of mine, John Huseman, has done a lot of work on this. I don't think he's talking at this Black Hat on it, when he's talking about EFI. He talked at last Black Hat about PCI rootkits. PCI cards support expansion ROM modules. These are mapped into memory by the BIOS and then executed. So, yeah, that's a good way. And the bbootkit and bootroot are CD-based attack vectors. These rely on the fact that if the BIOS is set to execute from CD first rather than the hard drive, then this code will obviously be executed. And EI's bootroot, as a proof of concept, just modified the kernel. So if you sent the kernel-specific packet, it would then blue screen, or they modified it so it would actually red screen. There is John has also done work on ACPI rootkits. So using the Advanced Configuration Power Interface, I think it stands for, provided by modern motherboards to interact with at a low level with the hardware and provide things the support things that are useful on laptops, such as the laptop powering off when you close the lid. That can also be leveraged at boot time to take control of the boot process. I have actually seen a couple of CPU errata that allow arbitrary code possibly to be executed on reboot, though I don't have a proof of concept for that, and I don't have the hardware to investigate it. There is one other way that I'm aware of. You can modify the BIOS settings, so change where the BIOS maps. Well, you can change where the actual BIOS is loaded from, so you can have user mode code, code you've written to a specific memory, and essentially tell the process to start executing from a different address on restart, so execute your code. Any other questions? Sure. So the question is, are there any other companies who are working on protecting the kernel in a similar way to PatchGuard? Not that I'm aware of. The closest I know of are the kernel-based access control systems. I'm not aware of... For Windows, it's always the issue that it's Microsoft-controlled code, so any third-party product is going to have difficulty interoperating with it. This is the reason why SoftICE has been one of the main... Detection of rootkit scanners. I'm not aware of anything that monitors the kernel itself. Everything I'm aware of deals purely with a user mode. Though if there are any, that would be interesting to look at, see how they go about it. Any further questions? Excellent. Thanks.